Today we will be discussing about regular falsi method. This is one of the method of finding the root of a transcendental equation. So in this method, at first we find a sufficiently small interval a0, b0 such that the sign at that point a0 and b0 of the function f are different. That is, f of a0 into f of b0 is negative. And also throughout this interval f dash x maintains the same sign. So by these two conditions, we can conclude from these two conditions, we can conclude that there exists only one root of fx equals 0 in that interval a0, b0. Right? As f dash x is maintaining the same sign, so there exists only one root of fx equals 0, a0, b0. So let's take the name of the root as alpha. Then f of alpha will be equal to 0. Now we have to find out that alpha or a near approximation of that alpha. So how will this method, this regular falsi method works? It works like actually the whole method is based on the assumption that the graph y equal to fx in the small interval that a0, b0 can be represented by the chord joining a0, f of a0 and b0, f of b0. That means suppose we have this graph position 2 dimension. This is our graph y equals fx. Okay, and this is the point a0 and this is the point suppose b0. Then join these two and this one. Now join the chord. This point is a0, f of a0 and this point is b0, f of b0. Now joining this chord. Throughout this procedure, throughout this method, we assume that this graph y equal to fx can be approximated by this chord joining a0, f of a0 and b0, f of b0. Okay, now we initially take the interval a0, b0. Now check the chord is cutting the x-axis at the point x1, right? This x1 is our first approximation of alpha because this is the root of that chord and we are thinking that the chord can be approximated to that graph. So this is our first approximation, this x1 of the finding root alpha. Okay. Now we got two intervals a0 x1 and we got two interval a0 x1 and the next one is x1 b0, right? Now for the next approximation, the root lies either in that interval or in that interval according as f of a0 into f of x1 is less than 0 or f of x1 into f of b0 is less than 0. Whichever is true, the root will lie in that interval either in a0 x1 or x1 in b0. Then we will do here from the graph we can check that the root lies here, that is in the next interval x1, b0. Then what will we do? We join this line again also. Okay, then the new point is that point and this point, right? Then again we will join the chord between these 2 points, that is x1, f of x1, this point and b0, f of b0, like this. Okay, then the chord is cutting the x-axis at that point, naming that point x2. This is our next approximation for the root alpha. Okay, now we will join again this point with our given curve. Then again we will join this point and b0, f of b0 to get a new chord. So by this iterative method, we will nearly approaching to our given root, which is alpha. Okay. So this is the whole procedure. Just take at first one small interval, depending on the sign of the at the end point. Then our root will lie on that interval. After that, we will approximate our given curve to the chord joining the end points. Okay. Then we will apply this iterative procedure. And for that iterative procedure we need some iterative formula because for that particular function we know the graph but for all the functions we always don't know the graph, so geometrical procedure isn't so easier for that. We need some iterative formula for some sequence, so let's find that. Now if I am drawing this picture again, it will look like this. One minute. This is our curve. At nth step, suppose this is a endpoint and this is b endpoint. Okay, joining these 2 points. So this point will be naming it as this one as P and this one as Q. The coordinate of the point P will be Bn comma f of Bn, and the coordinate of the point Q will be An comma f of An. Now check here, f of An is negative and f of Bn is positive. We have taken it like this. You can take the reverse also. And now joining the chord, it will look like this. The chord is cutting the x-axis at the point C, and we are naming this length, this An point to A, naming the An point as A. The point A to C, we are naming it as this distance, taking as Hn. Okay, so our first root will be An plus Hn, this length from the origin. This will be first approximation of our root. Okay, so from that diagram, what we can say, if we take 2 triangles, the triangle AQC and the triangle CBP, naming the point B. Okay, this small triangle and this large triangle, these are 2 similar triangles, so we can apply the rule here, that is AC by AQ. This length by this length will be equal to this length by this length, that is CB by PB. We actually want to find the root, first approximation of our root, right? That means this length An plus Hn. An, we know the point An. The unknown quantity is here Hn. So Hn means AC length. So from here what we can say, AC equals AQ into CB by PB. Now put the value AQ. For AQ, what will be the value? This length. This is the point x coordinate of that point, which is f of An, y coordinate of that point, which is f of An. So AQ will be the length of An. We are using the modulus sign because it is negative. We only need the magnitude, not the sign. Divided by PB. PB means this length, which is equal to f of Bn. So modulus of f of Bn into CB. CB can be written as, this quantity is CB. We are writing it as AB, this whole quantity, minus AC. Okay. So taking common AC on both sides, so it will be AC into 1 plus f of An by f of Bn equals modulus of f of An by modulus of f of Bn into AB. F of An by f of Bn into, what is the value of AB? It means Bn minus An. Take it. Okay. So AC, this length will be, this is actually our Hn. So AC equals Hn equals f of An modulus of into Bn minus An, just by after calculation, whole divided by f of An plus f of Bn. Modulus, obviously. So Hn equals this. This is the required value of Hn. Now xn plus 1 means, that is n plus 1th approximation. This is equals xn plus Hn. Okay. Now putting this value, we will get our iterative formula as xn plus 1 equals xn plus, not xn actually, an, that was the previous steps value, an plus modulus of f of an by f of an plus f of bn into bn minus an. This is the required formula. Okay, at the n plus 1th step of regular falsi method. Using this formula, we will find out the root of transcendental equations. Now clearly this is a sequence of xn. Using these values, there must be some convergence criteria of that method. So let's find out that criteria. Now, according as we have taken the sign of f of an as negative and f of bn as positive. So according as the sign, we can write the formula as, if you take f of an as negative and f of bn as positive, then the formula we can write it like this: xn plus 1 equals an minus bn minus an into f of an by f of bn minus f of an. We have chosen f of an as negative and f of bn as positive. According to our diagram, you can choose the reverse also, whichever you want. So the formula becomes like this. Now xn equals an or bn in any step, an or bn. Xn means the previous step's result, which is either an or bn. That means if it is whichever is negative, we will take this one, or whichever is positive, we will take this one. So instead of an, we can put xn. So xn plus 1 equals xn minus bn minus an by f of bn minus f of n into f of xn. Okay, so just putting this and this in one side. So we will get xn plus 1 minus xn into f of bn minus f of an equals minus bn minus an into f of xn. That is xn minus xn plus 1, just taking that minus over there. And over this part, f of bn minus f of an, we can apply Lagrange's MBT. Then it will take the value bn minus an into f dashed some xi n, where xi n will lie between bn and an. Okay, equals bn minus an into f of xn, where xi n lies between an and bn according to Lagrange's MBT. In the next step, we are introducing one alpha in that interval. That is, in that part we are introducing one alpha. We are writing it as alpha minus xn plus 1 minus alpha minus xn. F dashed xi n equals, bn minus an is cancelled out from both sides, equals f of xn. Now we are writing it as f of xn minus f of alpha. We can do that because if alpha is 0, alpha is the root of our given function. So writing it as f of alpha, extra one thing which is 0. Now over this part we are applying Lagrange's MBT again. Then we can write it as xn minus alpha into some f dashed xi n dashed, where this xi n dashed will belongs to xn and alpha, but we don't know which one is smaller and which one is greater than. So we are writing minimum of xn comma alpha to maximum of xn comma alpha, as we don't know which one is minimum and which one is maximum. So this value is equals to this. So from there we can write alpha minus xn plus 1 equals alpha minus xn into f dashed xi n minus f dashed xi n dashed divided by f dashed xi n. Okay. Now all the approximations lies between the initial interval that is a0 comma b0, and f dash x is continuous, so and it also has the same value throughout this interval. We have already assumed this before. That means there exist two numbers which must be one upper bound and one lower bound for f dash x, as it maintains the same sign throughout the interval. So there exists some lower bound and some upper bound for f dash x in that interval. That is, there exists small m and capital M such that modulus of f dash x will be lesser or equal to capital M and greater or equal to small m for all x belongs to a0 to b0. And since we are using modulus value, that means this must be greater than 0. Okay, now we will use that inequality over there. So we can write what we can write from the next line. We can write alpha minus xn plus 1, this modulus value will be less or equal to m minus small m by small m into alpha minus xn over modulus, right? Because we got in the numerator there was f dash xi n which is less or equal to capital M, because f dash x in that interval is less or equal to m, minus f dash xi n dashed. Now there is minus, that means minus of f dashed will be less or equal to minus of small m, so there is small m into 1 by f dashed xi n. That means 1 by f dashed is less or equal to 1 by small m, because we know the inequality change when we take either minus or we consider the reciprocal of the function. So this is why capital M minus small m by small m into alpha minus xn. Okay, now putting the value n minus 1 comma n minus 2 n minus 3 dot dot up to 2 1 0. Okay, and then multiplying, then all the term from this part and this part will be cancelled out, because if you put n minus 1 then it will become alpha minus xn, and from this part you will get alpha minus xn minus 1. Then from the next step you will get alpha minus xn minus 1 into alpha minus xn minus 2. Then that alpha minus xn minus 1 and xn minus 1 will be cancelled out. So after multiplying all these n plus 1 relations, we will get modulus of alpha minus xn plus 1 less or equal to m minus m by m whole to the power n plus 1 into alpha minus x0. Okay, now what is that quantity? This is the difference between our root and the n plus 1th approximation, which we are trying to get, n plus 1th approximation. That means this is our actual error, because this is the actual value and this is the approximated value. So this is our actual error. We can write it as xi n plus 1. Generally by xi n we denote the error. So from here we can write xi n plus 1 or epsilon n plus 1, whatever you want, equals, we don't use xi here because we already used for Lagrange's MVT one time xi, so better use epsilon. Epsilon n plus 1 equals alpha minus xn plus 1, which is less or equal to this quantity. Okay, now we are trying to converge this whole procedure, this whole sequence. So for that reason this part should tend to 0, then that alpha will tend to xn plus 1, that means our approximate value will tend to our exact value. So for that reason this part should tend to 0 as n tending to infinity. So what is the reason that this part should tend to 0? The reason is this quantity, there is power n, right, n plus 1 or n. Now whenever this quantity will be less than 1, then the whole quantity to the power n will tend to 0 as n tending to infinity. So the condition for the convergence is this part should be less than 1. That means m minus m by m should be less than 1. That is m less than 2m. This is the required criteria of convergence of the whole method. Okay, if this m less than 2m, then this quantity less than 1, then the right hand side is tending to 0. So the further convergence criteria of regular falsi method is that capital M should be less than 2m.